Okay, this is trig integrals, and this is really part two, and this one's going to focus on secant and tangent. Okay, as reminders, the derivative of secant is secant tangent, the derivative of tangent is secant squared, and the Pythagorean theorem says that tangent squared plus 1 equals secant squared. Again, just like before, this is going to give us the ability to change tangent squares into secants and vice versa. This is going to tell us which one's kind of du and which one should be the u. So let's look at this first example. In this first example, it's kind of just perfect for us because we have tangent cubed and secant squared. And I'm like, oh, wait a second. The derivative of tangent is secant squared. So if I make u tangent, du is just secant squared. And then it's kind of money because this one immediately turns into, well, this is just u cubed du. Boom, kind of done. Right? You love the fact that there was a secant squared. When you have a whole bunch of tangents, you want a secant squared there because that's what du is. And so then, of course, the integral of u cubed is u to the fourth over 4 plus c. And then you're like, well, I know what u is. This is just tangent. So this integral is tangent to the fourth over 4 plus c, and you're done. Okay, that was the easiest version. Okay, so what if there's not a secant squared out there? What if there's just a secant? Well, if there's just a secant, then you can't make u tangent because you're never going to get this secant squared for your du. Well, what if I rip off a secant tangent? Because I know the derivative of secant is secant tangent. So let's take this guy and take a tangent and a secant and put it off to the side. That would leave this as tangent squared. And I'm going to take this off to the side and have a tangent and a secant chilling out over here. Okay, I have the vision that eventually that's going to be my du. Like, well, that's not the derivative of tangent, that's the derivative of secant. But I can use this to rewrite tangent squared. So this allows me to say that tangent squared is secant squared minus 1. And then over here is just tangent secant. Okay? This then is u squared minus 1 du. And it really turned out to be that easy, right? If u is secant, you can go ahead and write it if you need to. If u is secant x, then du is secant x tangent x dx. So that's u squared minus 1, and then this whole thing is du, and we kind of knew that, right? We ripped off a secant and a tangent, knowing that we were going to take tangent squared, rewrite it as secant squared, and so we were going to have a bunch of secants with their derivative secant tangent. And so then we have the integral of u squared, which is u cubed over 3. The integral of negative 1 is just negative u. And then we just put in exactly what we know. Secant cubed over 3 minus secant x plus, I guess there should have been plus c up there. Okay, and if you get a little lost, you can always just make sure that if you take this derivative, you get back that original one. But so we ripped off a secant tangent, we changed the remaining tangent squares into secant squares, and then we go ahead and did a u substitution. Again, all of these, maybe I should have wrote this up here again. On the first video, I reminded you that all of these trig integrals are really just power rule things. You're using these facts to rewrite trig integrals as power rules. Trig integrals as power rules. Okay? What about this next one? Tangent cubed, secant cubed. Well, if you tried to think of this, if you took out, bring out to the side a secant squared, well, you'd only leave a secant, and you can't change secants into tangents. So this one's not going to work. You're going to have to do this guy. Okay? Go ahead and take out a secant tangent, and then it'll be just fine. It'll be very similar to the last one. Okay? This, and this will almost be identical. Leave a tangent squared, leave a secant squared, and then what we did was we factored out a secant and a tangent. Okay, we ripped off a tangent and a secant, put them off to the side, and we're left with tangent squared and secant squared. If we rip this off, we're anticipating this being our du. This is the derivative of secant, which means you got to change this into secants, and this ends up being, like I said, almost identical to example number 2. Take these tangent squares, write them as secant squares minus 1. This is just secant squared. This whole thing is still just secant tangent. But then we know that this really is u squared minus 1 u squared du. This is du if u is secant. So this is secant squared, or u squared minus 1. So this then is really just u to the 4th minus u squared du, and we've successfully converted a trig integral into a power rule. Power rules are easy. U to the 5th over 5 minus u cubed over 3 plus c, but then u is secant, so this is just secant to the 5th over 5 minus secant cubed over 3 plus c. Okay, so in this case, I ripped off a secant squared and had tangents. Both of these cases, I ripped off tangent secant or secant tangent because I couldn't take out a secant squared because I had odd versions of secants. Okay, how about this one? What would you do on this one? Well, this one you're not going to rip off a secant tangent. If you took off a secant tangent, well, actually, in this particular case, you can do whatever you want. Both methods will actually work here. You could take off a secant tangent, and that would leave you with a tangent squared and a secant cubed. You could change the tangent squares into secants and go. Or you can rip off secant squared. Let's rip off secant squared this time. This one is your choice. So it's that tangent cubed, secant squared, and then I'm ripping off a secant squared. Okay, so I'm going to park this guy over here. That's going to be my du. Remember, secant squared is the derivative of tangent, so then I'm just going to write all of these as tangents. But that's okay. Tangent cubed x, and then instead of this secant, I'm going to write it as tangent squared plus 1. But now I'm golden because this is u cubed times u squared plus 1 du. This is my du if my u is tangent. I took these secant squares, rewrote them as tangent squares, and now what I have here is then the integral of u to the 5th plus u cubed du, which then I know is u to the 6th over 6 plus u to the 4th over 4, but I know u is tangent, so this is tangent to the 6th over 6 plus tangent to the 4th over 4 plus c. Okay, so if tangent is odd and secant is even in terms of their power, then you can actually do both methods. Okay, now this one down here, not cool. Not cool at all, because look at it. If you try to take out a secant squared, I want to show you why this is unsuccessful. If you tried to rip off a secant squared x, okay, you tried that, you'd have to change all of these to tangents, but you just have one secant here. You can't change this to tangent, right? That's going to mess everything up, so that won't work. So instead, you look back at the original, what if you tried to rip off a secant tangent? Well, if you ripped off a secant tangent, then what would you be left with? Okay, so rip off a secant tangent. Take away one of the tangents and one of the secants. You'd be left with tangent secant. But if this is your du, then you need u to be secants. So you need to change this to secants. But that's just one tangent. You can't change one tangent into secant. So that one's not going to work. That's why this method, not cool. Okay? The only thing you can do here is you actually change tangent squared from the get-go to secant squared minus 1. Then you get something that looks like this. And then you'd integrate secant to the 5th x minus secant cubed x. and then you'd look up what they call a reduction formula. So this is straight up, you'd have to look it up in a book. I don't know anyone that has these reduction formulas memorized, but it would tell you how to integrate just secants. So you'd look up the reduction formula for secant to the fifth and a similar pattern for, or the same pattern for secant cubed. Okay? Not on any test I've ever seen. Not on any college test, unless they just gave you the reduction formula on the test. But there's certainly no reason to memorize this. You should know, however, if I give you one of this, why this one is in the not cool category. Again, an even tangent and an odd secant is going to create the scenario in which both of these don't work. As long as secant's even, well, then you can do this. If tangent is odd, you could still do this method and rip off a different one. Okay? But if this is even and this is odd, not cool. Okay, and again, it's not on my test, it's not on the AP test, it probably wouldn't be on any really college midterm test unless they gave you the reduction formula.